Hi, good day everyone. My name is Abhilash, and today I will be speaking about multi-scale numerical modeling of porous composite structures. I hope you enjoyed this discussion and find it useful. Here is a brief summary of this presentation. First, we take a look at the motivation and the background for this work. Then we move on to upscaling methods such as the multi-scale methods, further to virtual element methods. Then we combine both of these together to obtain a multi-scale virtual element method. We further investigate some. Alright, first we have a look at the motivation. Composite structures on their own are found to show good structural performance but poor vibroacoustic performance. It has been found that coupling this with poroelastic segments yields multi-layered systems which have augmented structural properties as well as vibroacoustic properties. This motivates the investigation of further composite structures such as the following. Well, this is an example of a multi-layer panel, and let's have a look. Yep, here is an anechoic wedge with inclusions. That is, we've got mesoscale pores and solid inclusions, and these are found to augment sound absorption, especially at lower frequencies where traditionally it has been difficult to achieve good performance. This is an example of a porous composite with tortuous mesoscale inclusions. That is, we've got an axial perforation with some tortuosity, and there is a client and a host material there as well. Moving on. Composites often come with anisotropic and highly heterogeneous mechanical properties and can be engineered to tessellated geometries to optimize performance. The question remains that is it possible to account for such aspects within a rapid and accurate simulation framework? The answer is, we will see in a second, yes. Another motivation is concerning data-driven models. Typically, a model works as follows. One has an input excitation. This could be a load or an acoustical plane wave, for example. This is passed into a mathematical model, which is informed by physics. These are typically partial differential equations or integral equations. And these, after solving, give us an output or a response. However, in the case of data-driven models, these outputs generated from the mathematical models can be used to inform our so-called meta or surrogate models, which are further informed by AI and trained to obtain, maybe if it's a neural network, we can obtain some optimal weights and so on. And this instead can be used to predict the output and response. Now, what is the difference in terms of performance between both these approaches? We will have a look. We divide the performance into two phases, that is the offline and the online. Offline typically contains training purposes, and of course, in a case of a mathematical model, there exists no such training phase. However, in the case of a meta model, yes, one has to train it, and this can be expensive. This is because of the curse of high dimensionality. That is, a huge training set is required to be sufficiently representative of the physics. However, in the case of online purposes, that is the place where solving occurs, one can see that the mathematical or physics inspired model can be quite slow. However, the meta model comes into its own here and generates outputs almost instantaneously. The question remains now that is there a cheaper way to generate this training data? And the answer is, of course, yes. We now take a look at multi-scale models. Why multi-scale models? Well, we've got a structure that exists at three scales. A macroscopic scale, which is the structural behavior, the resultant material, for example, the grains and so on. This is at the mesoscopic scale, and the actual constituents. For example, in the case of a porous material, we have complicated porous networks. This exists at a microscopic scale. We need mathematical models to account for these effects across different scales. Hence, we have the concept of multi-scale models. This is an example of a picture where upscaling happens. This is a multi-scale domain. You can see that there exists meshes at two levels, at a coarse level and at a fine level. Each coarse element, or RVE, is clustered. It clusters its underlying heterogeneity, which has a particular microstructure, as you can see here. Basis functions are clustered and evaluated over this, as can be seen in this picture, and then they are upscaled onto a coarse scale where the solution is evaluated at reduced cost. Why do we need all this? As I've already mentioned, resolving fine scale heterogeneities yields a large number of degrees of freedom, and it can be computationally expensive. Hence, upscaling is desirable. Next, we move on to multi-scale methods. Now, we ask ourselves the question, what multi-scale models do we use? It is worth noting that at the moment we are interested only primarily in phenomenological models, i.e. macroscopic models. We are interested in coupling macro and mesoscales, where mesoscale is an artificial scale introduced for accelerating computational costs. We're currently not interested in microscale effects at the moment. Here we're going to be using a family of heterogeneous multiscale methods, although this isn't the heterogeneous multiscale method. This is a slightly different one called multiscale finite element methods, or MSFEM for short. We take a look at the equations we'll be handling in this presentation. First, beginning with poromechanics. Here is the BOUP, that is the displacement pressure formulation for consolidation in poroelastic materials. On the left, we've got a divergence, basically a diffusion term of the elastic skeleton. On the right, we have a source term, basically, where U denotes the displacement or the solid phase, and P is the pressure or the fluid phase. B is a body force. This is the momentum balance similarly for the fluid phase. The right side is primarily the Darcy law and so on. You can notice that it is a time-dependent equation. And we don't need to worry too much about this, but we got the abstract weak formulation of the same here. It will come in handy for us later. I just ask you to remember these two terms. We'll come back to it, of course. The first one being a epsilon of u comma v, where v is the weighting function for the displacements. And similarly, a nabla of p comma w. Similarly, we take a look at the UP formulation for wave propagation in poroelastic media. You will notice that it is almost the same. However, we have also a mass term or an inertial term for the solid phase as well. And the entire equations are cast in the frequency domain through Fourier transforms. Again, we've got the abstract weak formulation where we are primarily interested in two terms here, A epsilon and B nabla. Now, let's look at the operation flow of the method. Let's load it. Just give us a second. All right, this is a flow chart. Never mind. Right. So one uses the finite element method to compute RVE equivalent stiffness matrices over each RVE, as I've just mentioned. This leads to numerically evaluated multiscale basis functions. These functions are used to upscale the equivalent stiffness matrices. Then the solution is performed at the core scale and further downscaled using the multiscale basis functions. How do we evaluate these basis functions? We look at them in more detail. Now, this is an example of a highly heterogeneous domain with two levels of meshes. We've got a fine scale quadrilateral mesh, and on top of that overlaid with a coarse quadrilateral mesh where each coarse element clusters its own individual microstructure. By solving an individual cell problem, as we will see in a second, one results in these extremely flexible basis functions n1 through n4, which account for the underlying oscillation in material configuration. This is basically understood as a more flexible alternative to standard finite elements. Right. So we compute the basis functions in a decoupled format, one set for the solid phase and one for the fluid phase. The solid phase is computed as follows. We evaluate a homogeneous version of this equation, that is A epsilon equals 0, and the solution to this equation is subject to certain kinematical constraints, and the Nu denotes the multiscale basis functions for displacements. Similarly, we do the equivalent for the fluid phase, and this time we solve the equation A nabla and assign the same periodic or oscillatory or linear boundary conditions as I mentioned here. So we've got linear, periodic, oscillatory, and oversampling. It is important to note that these boundary conditions are critical to the accuracy of the method, and one needs to take care while imposing them. We now take a look at a problem pertaining to vibroacoustical applications. Here is a schematic of a material placed inside an impedance tube configuration, where PE denotes a poroelastic material. We have four boundaries. The top and the bottom in this case have sliding or rolling supports, and at the back one can either have rigid or impedance boundary conditions. On the front, that is gamma 1, we've got an acoustic plane wave or diffuse field excitation impinging. As I mentioned, we already have sliding boundaries. One can consider multi-layer configurations if they choose. The air has ambient air conditions, and this concerns the termination over here on gamma 3. It can either be rigid or anechoic. And one can compute different acoustical indicators like absorption coefficient and transmission loss coefficient. Or regarding the modeling side of things, we can consider elastically deformable skeletons and rigid motionless skeletons as well. We will see later on that we can use different kinds of mesh. Here's an example of a double porosity medium. By double porosity, we mean that there is a perforation at the mesoscopic scale. This is the 2D version and the 3D version. You can see that the material used is melamine foam, and it is modeled using the Johnson Shampoo Allard 5-parameter model. We consider non-dissipative air here. For purposes of comparison, we use the finite element method, multiscale finite element method, and the transfer matrix method. Two sets of discretizations. For the 2D mesh, we've got 4 quadrilateral elements at the fine scale, that is per RVE, and at the 3D finite element method, we've got 8 hexahedral elements per quadrilateral coarse element. Here are the sound absorption coefficients obtained for each material model. For the rigid skeleton model, we've got this, that is the curves obtained by 2D, 3D, the transfer matrix method by mixing law, which is basically an averaging of heterogeneities at the fine scale, at the mesoscopic scale. And then one has the reference transfer matrix method. We can see the same thing in the elastic case model. In the elastic model, we can see that there is a quarter wavelength resonance here as well. Now, the 3D model and the transfer matrix method match reasonably well. And similarly, the 2D and the transfer matrix method mixing law, well, the trend is replicable, but the values do not exactly coincide. This is attributed to the fact that we're using square cross sections here, whereas the axisymmetric model used in the reference transfer matrix method solution was, well, it was axisymmetric, so you need a cylindrical geometry. The same thing applies in the case of the elastic skeleton model as well. Now, regarding the speed ups, we check out the comparisons between the finite element method and the multiscale finite element method. You can see in the case of 2D, there is a speed up of 3.22, and in the case of 3D, there is a speed up of nearly 29 times. Now, we've had a look at the multiscale finite element method. Let us revisit this very briefly by comparisons with other methods like the standard FE square method. In the FE square, how it works is that one takes an RVE and constructs it at the core scale in a standard finite element procedure. However, at the integration points, we are currently unaware of a constitutive law. Hence, with each core scale integration point, one attaches a micro mesh where FE computations are again performed. These micro mesh computations are then homogenized using volume averaging and then mapped onto the core scale through energy equivalence. And then we can compute this. However, multiscale finite element method, you will see, differs from this in the following. No homogenization is performed, that is, direct upscaling is done. There are no requirements on scale separation or periodicity. Further, the mesoscale heterogeneities are mapped onto the microscale through multiscale basis functions. This allows for downscaling as well to ensure that no fine scale info is missed. These multiscale basis functions are numerically obtained by solving the partial differential equation over an RVE. What are the limitations of the multiscale finite element method? It has so far been implemented only for quadrilateral or hexahedral coarse and fine elements. But what about these cases? In the first picture here, you can see that the fine scale has a complex morphology, and this can be efficiently meshed with polygonal elements, as noticed here. And in the second case, we have a complex geometry which has, well, a non-convex RVEs, which are quite complicated. The multiscale finite element method, as it currently stands, cannot handle either of these. This is motivating us to check out polygonal methods, and we have a look at the different polygonal methods available to us. First, we have a scaled boundary finite element method. This involves mapping each element onto a polar coordinate system where one has radial and tangential coordinates, and it turns out that the FE solution along the radial direction can be analytically determined. So one is left with discretizing only the tangential direction in finite element style. This reduces the dimension of the problem by 1, the physical dimension, and can be very useful. Then we've got cut FEM. This is similar to immersed boundary method style. One has polygonal finite element methods where the whole problem deals with defining appropriate shape functions for polygons, and then the virtual element method. The point of departure of the VEM from the other guys here is that the scale boundary element method only works for star convex elements, and the polygonal finite element method can work for only convex and possibly star convex elements. However, the virtual element method can work for non-convex as well, as we will see in a second. Why VEM? The main problem is generalizing defining shape functions for generalized element shapes. This is not possible because one cannot have analytic shape functions for possibly non-convex things unless one deals with polygonal finite elements. And this is an active area of research. The VEM does this by avoiding explicit definition of canonical shape functions altogether. This works for generalized polygonal elements including non-convex, as I've already mentioned, and it can work for arbitrary polynomial orders too. How does the VEM discretization work? We begin with a finite dimensional approximation as follows, where the displacement is approximated with a finite dimensional version, and so is the test function. Similarly, the pressure and its associated variations, or the test function in this case, has been approximated. How is it approximated? Well, we discretize it with canonical shape functions phi u and phi p. Similarly for these guys, it is critical that phi u and phi p are left unknown. At least we do not have an explicit expression for them. Rather, they are implicitly defined through their degrees of freedom. Then we will do some intelligent manipulations in order to obtain certain properties. Now, given a non-convex element like this, we will try out a kinematic decomposition. That is, the complete discretized displacement field is split into a polynomial component and a non-polynomial component. This will help define the bilinear forms in a more efficient manner. How do we define the polynomial components? These are obtained through a projection onto a polynomial space, where the projection is done to this operator pi k. Similarly, one has the same behavior for the pressure fields as well. These the polynomial fields, that is pk squared and pk, are vector and scalar polynomials defined over the element. So look, right, and these operators pi k are operator specific. That is, for the epsilon operator we have a different projector. For the mass matrix we have a different projector, and so on. So these are solid specific ones, and these are fluid specific guys. These need to be defined using an orthogonality condition. Now, once we have the projectors, we can split all our bilinear forms, all our energy formulations, into a corresponding polynomial and a non-polynomial component like this. So these are just generalized formulations. Yeah, polynomial and non-polynomial. Now the polynomial on its own are rank deficient over the polynomial spaces. This is because we have neglected certain non-polynomial modes. So we can understand this non-polynomial component as a stabilizer, that is, it restores cohesivity. This part, the polynomial guy, can be computed exactly because it consists of only consistent kinematic modes, whereas the non-polynomial part cannot be computed at all, primarily because we do not have the expressions for pH, delta UH and delta pH. This is called the consistency term, and this is approximated by the stability term. We apply the virtual element method discretization schema to a multi-layer system here. This is just an arbitrarily chosen multi-layer system, where the first one is a melamine foam, the second is a plasterboard, and the third is air. Now I zoom in on the interface, and you can see here in the first picture that the interface is non-conforming. With the advantage of polygonal elements and the virtual element method, all hanging nodes can be resolved by treating it as just an additional edge, as you can see over here. So this gives us an easy method to resolve non-conforming interfaces. This is the sound absorption coefficient obtained at normal incidence, and the sound transmission loss obtained at a diffuse field. You can see that the results between the virtual element, finite element, and transfer matrix method match reasonably well. Now, the next example is a case of porous composites as follows. You can see that this has a poorly resolved interface. This is to study the influence of imperfect interfaces on the sound absorption or transmission coefficient of the problem. In this case, it turns out that it is not very sensitive, and we get perfectly corresponding results for all three methods except at higher frequencies, of course. And these are the contours for these are the pressure contours at a high frequency for virtual element methods and for finite element methods. Now we move on to multiscale. The multi-scale virtual element method allows for flexible discretizations at all scales. As you can see, one can accommodate complex geometries at the coarse scale, the fine scale, that is the mesoscopic scale, and the fine scale. This is very similar to the multi-scale finite element method, except that at the fine scale, the virtual element method is used to compute the multi-scale basis functions instead. This is, as I mentioned, allows for complex fine scale descriptions and generalizes the computation. Now let us investigate further functions for non-convex RBEs how one travels across the scales. This is primarily based on a principle of energy equivalence, sometimes called the Hill-Mandel principle in Fe squared or heterogeneous multiscale methods and so on. This is the basic idea is that the energy at the coarse scale is equal to the sum of all the energies at the fine scale. This is the idea. This is done for both the solid phase and the fluid phase. Similarly, using the same philosophy, the field variables, that is the microscale displacements, are upscaled to the macro scale, and similarly the microscale pressures are upscaled to the macro scale. Once this is done, the solutions are performed at the coarse scale at reduced cost. Further, it can be downscaled using the same relations mentioned here to obtain fine scale information at, almost for free, one would say. Of course, it is not technically for free. And one can obtain post-processed results like acoustic indicators, stress, strain relations, and so on. Let us look at an example applied to a fiber reinforced composite within the realm of elastostatics. So you can see that there is a cantilever beam subject to a transverse load over here. This has got a periodically repeating unit cell composed of a stiff inclusion and a softer matrix. Their respective Young's modulus and Poisson's ratio are given here. This microstructure is meshed with three types of meshes using the multiscale virtual element method. The first is a quadrilateral mesh. This serves as a reference solution. The second is a centroidal Voronoi tessellation mesh, which is filled with uniform polygonal elements, as you can see here. And the third is an ad hoc mesh designed specifically to exploit the benefits of the virtual element method. Namely, the central element is a 252-sided element, exploiting the stiffness of the inclusion. This is an adaptive mesh. Now, these are the von Mises stress contours provided by the FEM and the VEM and the MS-FEM. And the MS-FEM solution has been provided for the third mesh, the adaptive one. Periodic boundaries are used for the multi-scale solution. Accuracies of mesh 2 and 3, that is the CVT and the polygonal mesh, are compared against the reference mesh 1 solution. Here one can see that the error norm obtained by the CVT mesh is quite comparable to the error norms obtained by the polygonal mesh, both the L2 and the H1 error norms. However, there is a significant reduction in complexity compared to the reference. That is, the CVT offers a 29.33% reduction and the polygonal mesh a much higher percentage. This shows that one can significantly exploit the power of the VEM at the fine scale to drive down computational cost. We now look at another example. This is in the realm of poromechanics, more specifically consolidation. We consider a heterogeneous soil domain and mesh it at two scales using these two possible meshes. That is, the first one has a quadrilateral mesh at all scales, and second has a polygonal mesh at all scales. We're interested in investigating the evolution of displacements and pressures at the 3 points A, B, and C. These are the boundary conditions: zero pressure boundaries, zero flow boundaries across all edges. There exists a compressional load at the top. And as I mentioned, we're interested in the displacement and pressure evolutions. This is a highly heterogeneous domain. For the fluid phase, we have a permeability field sampled randomly from a log normal distribution. Similarly, a highly heterogeneous Young's modulus as well. These are just samples. Monte Carlo simulations are performed for these random fields, and the time evolution has been plotted as an expectation over 1,000 samples at the 3 points. Let me just get all the figures on screen and I speak about them. All right. Now, the first row corresponds to the evolution of X displacements, Y displacements, and pressures at point A. The second, similarly for point B and for point C. Remember that point A lies in the center, and so it is expected, points A and C, they lie at the center. So according to symmetry, one would expect that they show very less X displacements, right? The minor deviations are due to Poisson effects, of course, and asymmetries in the mesh and material configuration. The other behaviors you can see are exhibited for MSVM quadrilateral with linear boundary conditions, polygonal with linear boundary conditions, quadrilateral with oscillatory, and polygonal with oscillatory. And the finite element method is treated as a reference. Just to clarify, the E over here stands for extended multiscale finite or virtual element methods. I would suggest not to worry about that too much. The extended just says that it accounts for, well, Poisson effects. It's a structural mechanics concept. Anyway, you can see that there is significant agreement between all methods. And here's a look at the contours. These are the displacement contours obtained by MSVM quad oscillatory, MSVM polygonal oscillatory, and finite element reference solution. You can see they are nearly identical. Similarly, the pressure contours also seem to agree quite well. This is, by the way, at the time instance t equals 25 hours. The MS multiscale solutions are interpolated at the coarse nodes for visualization, and no downscaling is performed. We now take a look at the computational times taken by the method in greater detail. We first take a look at the picture on the top right concerning the assembly time. This involves processes like the multiscale basis function evaluation, upscaling, and assembly of the coarse and fine scale stiffness matrices. As expected, we can see that the fine scale methods without upscaling take a lot longer than the multiscale methods. Now next we take a look at the solving time. Once again, since the solutions are performed at the coarse scale, it is obvious that the multiscale methods would be much faster than the methods without upscaling. Next, we have a look at the post-processing times, that is times required to downscale and compute acoustic indicators, for example, or stresses, strains, fluxes, gradients of pressure, so on. These quantities once again are shown to be quicker within the case of multiscale methods and slower otherwise. We put all of them together just to make sure that no significant overheads are experienced by the multiscale methods, and yes, you can see that there is acceleration. We now investigate the potential of using flexible RVEs in our method. Now we have, let me get my laser pointer back on. Here we go. Right, this is an example of a porous material with a rigid skeleton and an infinitely rigid inclusion, circular one, that is repeating periodically. This can be meshed at two scales using the multiscale virtual element method. At the coarse scale, we can employ coarse elements that look like this. Let us first take a look at number one. And these are the sound absorption coefficients obtained by using RVE number one. However, RVE number one can be used at different levels of fidelity. By this, I mean this corresponds to the total number of coarse nodes one has per element, starting with RVE 10 corresponding to the lowest fidelity and RVE 13 corresponding to the highest number of coarse nodes. Now, one can see that at low frequencies, yes, the trend is reasonably replicated, although the peak is slightly overestimated by the numerical methods as compared to the reference solution here. And beyond 6000 Hertz, none of the methods offer reasonable behavior. Even the highest fidelity solution, yes, it does increase, but it is nowhere near accurate. This is simply because we do not have sufficient number of coarse nodes required to resolve the high frequency waves. This allows us to move on to RVE number 2, where we split it down the middle and we get two non-convex RVEs. This allows us to have coarse nodes along the circular interface as well, overall allowing us to have more number of coarse nodes. And you can see accordingly the solution has improved, especially in RVE 2.3. We see that although the solution is not perfect, an increasing trend is observed. So to make sure that the solution converges, we further split it down the middle to obtain 4 non-convex RVEs as follows. And now we can see that at RVE 3.3, that is the highest fidelity case, the solutions nearly exactly correspond. This allows us to have a significant acceleration over standard finite elements. The pressure contours are provided for reference. The VEM, let me just get my pointer back on. Right, this is the pressure contour at 10 kHz as provided by the VEM. Next, we have it as provided by RVE number 1 at the highest fidelity case. You can see that the black nodes correspond to coarse nodes, apologies, and the contours are significantly incorrect, as can be seen here. Next, we take a look at RVE 2.3's solution, and again the solution is still incorrect, but yeah, I mean there is no other question to it, and there are coarse nodes across the interface in this case as well. And now in the final case, we have coarse nodes applied everywhere, including the interfaces here. And this allows us, of course, you can see the contours now nearly exactly match. We investigate model order reduction. The motivation for this is that since the acoustical problem is a nonlinear one with respect to frequencies, one needs to repeatedly evaluate multiscale basis functions at each and every frequency. When the microstructure is really detailed and with fine discretizations, this becomes very computationally expensive. One requires some methods that can accelerate these multiscale basis function computations. For this, we investigate reduced order modeling through snapshots. The problem we are going to be investigating is proper orthogonal decomposition. To begin with, a random solution Z, which is made of is a function of displacement and time, is discretized into a finite dimensional approximation with time-dependent scalars and orthonormal basis functions. This is just a choice. It does not necessarily have to be orthonormal. Now, the question remains, how do we evaluate these basis functions? The numerical choices for phi, the more popular one is proper orthogonal modes. This is what we are going to investigate at the moment. You can notice that the proper orthogonal modes dimension n is identical to the total dimension of the problem. However, to obtain some speed up, we want to have a reduced dimensional representation with dimension r, where r is significantly lesser than n. That is, we want to pick r modes from this matrix and use that to represent the solution as accurately as possible. Now the question is, how do we find this reduced basis? The goal of the POD is obtaining a reduced proper orthogonal basis such that the error between the approximation is minimized. To compute this, we first obtain a snapshot matrix. That is, we randomly select m different points for sampling and obtain full fidelity solutions at these points, where m denotes the total number of snapshots. These are stored in a snapshot matrix Z. The snapshot matrix Z is now decomposed using the singular value decomposition, or SVD, into the following. Into an n by n orthonormal matrix containing left singular vectors. Give me a second. Then an m by m orthonormal matrix containing right singular vectors, and an n by m pseudo-diagonal matrix pivoting the singular values of Z, that is sigma ii. This can be understood to be a generalization of an eigenvalue decomposition, but for rectangular matrices as well. Now the sigma ii singular values are sorted decreasingly, where sigma ii squared is a measure of energy along the orientation direction, and one arranges L and R accordingly in that rearrangement. Now the first R columns of L constitute the optimal reduced POD basis. Now the question goes to, how do we choose this reduced dimension R? The answer is very simple. It is basically using a truncation criteria based on a modal participation factor, where P is the desired accuracy of the reduced order solution. We plot this ratio of the POD method is now used within the context of a multiscale method to obtain a reduced basis multiscale approach. The fine scale solutions UH and PH are expressed as in the form of a proper orthogonal mode basis as shown here. How do we compute these bases? Well, we obtain snapshot matrices at the fine scale for each RVE, for each of these guys U and P, at a set of M frequencies which are randomly sampled. Then, as mentioned before, we do the truncated we do an SVD approach. I mentioned a truncated SVD approach because SVD operations can be a little expensive, especially computing the singular vectors and so on. There exists a way to reduce the cost of this operation by only evaluating the first, 10, 15 or 20 singular values. This is called a truncated SVD. So, all right, you are performing the singular value decomposition. We can obtain proper orthogonal modes, the reduced versions shown here. Similarly, the same thing is done for pressures as well. Now, this is all the bilinear terms involved are projected onto this reduced dimension subspace using the proper reduced basis, and then can be evaluated at a reduced cost as shown here, because the reduced basis is also a projection, as can be seen for the solid and the fluid phases as well. And now we can evaluate these quantities in an accelerated fashion. Let us show an example of POD first without the upscaling, and then I show it with upscaling. This is done for a standard poroelastic media, a rectangular domain. It has been meshed for a reference case with 2500 quadrilateral elements that corresponds to 7803 degrees of freedom. To compare this with the reduced order model, we've used a 10 degree of freedom reduced order system. That is, it has 10 POD bases. How do we determine that only 10 are sufficient? By plotting the singular value decay as mentioned earlier. This wherever a neck occurs, one can assume that, well, this is a heuristic. One can assume that one has enough number of singular values, and beyond that, the proper orthogonal modes do not contribute much. So one can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 singular values, and this gives us an accuracy approximately of 10 to the minus 16. Now, we also have a lo-fi model just to illustrate the accuracy of a reduced order model. This lo-fi model is based on a standard finite element model without any model order reduction strategies. This has only a single quadrilateral element comprised of 12 degrees of freedom. Now we take a look, we can notice that the full order model is identical to the reference solution across the entire frequency spectra, and so is the reduced order model. However, the lo-fi model has good accuracy only up till, well, until 1000 Hertz. Beyond that, it is unacceptable, simply for the reason that the bases are not rich enough to resolve high frequency waves. There are 100 frequency steps mentioned here. The sound absorption is called, the full order model, reduced order model, and transfer matrix method, as I've mentioned over here, are identical. Lo-fi offers only good approximation at low frequencies, which is a reiteration of what I've already mentioned. Now let us take a look at the UX, that is the displacement along X contours at a particular frequency at 5000 Hertz for all three methods, and similarly the pressure contours. Let's look first at the displacement contours. You can see that the full order and reduced order model contours are identical, whereas the lo-fi is not. Similar behavior is observed for the pressure contours as well. The lo-fi models are noticeably inaccurate, as I've already mentioned. The ROM are practically identical to the full order model. When we compare between the reduced and the full order model in terms of computational complexity, the reduced order model offers a 72.31% speed up and an associated 99% reduction in dimensionality of the problem. We now apply this into a reduced base multiscale context, where once again we have a poroelastic material with anechoic termination this time. It's a highly heterogeneous medium, so it's got a Young's modulus as follows and a static airflow resistivity. Since it's highly heterogeneous, we require a fine discretization to accurately resolve all heterogeneities. The pressure contours as obtained by the WEM at 5 kHz are provided, and also by the MSWEM and the reduced basis MSWEM. We can see that they are almost identical throughout, and so are the sound transmission loss contours obtained by all three methods across all frequencies. Now we further take a look at the computational times, first at the fine scale. We take a look at the WEM complexity first, then the MSWEM, and then the reduced basis MSWEM. For the reduced basis MSWEM, a few factors need to be considered, particularly the time taken for evaluating the POD basis. This typically comprises the singular value decomposition and the mapping onto the reduced basis subspace, the MS basis computation time, and the assembly. As expected, the MS basis assembly time of the reduced method is much lesser than the MSWEM. This was our initial motivation, and it is also good news that the POD basis computation time is not all that expensive. Of course, this needs to be done carefully. For more complex problems, one might require a larger POD basis, that's compromising the efficacy of the method. All in all, both methods are significantly faster than the WEM. We now look at the core scale solutions. Here, core scale time is taken. These are the main bottlenecks are pre-processing, solving, and post-processing. Here, once again, the reduced basis method is the quickest, and then followed by the multiscale method, virtual element method, followed by the virtual element method, that is without upscaling. Now, in terms of speed up, we can see that the MSWEM offers a speed up of 7.75 over the WEM. The reduced basis MSWEM offers a speed up of 11.97 over the WEM, and also a 1.55 over MSWEM. Now we make some concluding remarks. Let me just get all the remarks on the screen. The method MSWEM is a method for handling heterogeneous morphology. It offers a significant reduction in computational time compared to virtual element methods. It has been implemented for elastostatics, poromechanics, that is bioconsolidation, and vibroacoustics. and shows good correspondence with finite elements, virtual elements, analytic, and transfer matrix method results. Exist several future stakes. The first being concerning the vibroacoustics of multi-layered systems. This is something that ESR number 2, Arasan, works on. I will let him explain this in greater detail. Then we have got the dual porosity and mesoscale intrusions, that is taking what I have worked on and extending it to further complex examples with such complicated geometries, graded mesoscale porosities, and so on. The third is concerning acoustic and structural topology and shape optimization. This is something that ESR 3 Vivek works on, and he will be able to explain it in greater detail. The fourth concerns micro-macro multiscale approaches, that is mapping effects at the micro scale, for example, solving the Navier-Stokes equation in the frequency regime and mapping it to macroscopic parameters such as porosity, tortuosity, or static airflow resistivity, so on. With this, I come to the end of my presentation, and I would be happy to answer any questions you have. Thank you.